Okay, so I think, can you hear me? Hi, Andre. Yeah, good morning. Yeah. Let's start. So, good morning, everyone. Thank you for coming to APCTP Colloquium today. The speaker of today is Professor Andre Bernevig from Princeton. Professor Andre Bernevig has made numerous periodic and systematic contributions to the field of topological and strong correlated materials. So, Andre, so you can start. Yeah.
Good morning, and thank you so much well, I guess it's 10 a.m., so it's not that early, but thanks for waking up and showing up to this colloquium. Can I just share the screen now?
Oh, yes, 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 yes.
Okay, very good. Sorry, 1 second. Let's see. Can you see the entire screen?
Yes, yes.
Okay, very good. So I guess in these 50 minutes or 45 minutes, however many I have, I want to present to you several developments that have happened in my field, which is condensed matter physics. Um, they have to do with kind of the alchemy of material science today and how we build materials and quantum states of matter today. So the title of the talk is basically Moire from topology to interactions, and I'll hopefully convince you that this is a phenomenally exciting field where we can kind of um, construct materials, engineer materials as quantum simulators of basically almost any Hamiltonian we want to build. So the reason why we're physicists, and really this transcends condensed matter physics, the same for astrophysicists, string theorists, and other types of physics, is because we really want to understand what the world is made of. And in condensed matter, or in my field, we can ask another question than just understanding what the world is made of. And this question is, what can we make out of the elements that have been given to us in this world? Meaning, what type of systems can we put together and make in a laboratory? This is kind of what distinguishes my field from others, the fact that you can actually play around and make new things from what you have in nature. And then once you've made these new materials or these new quantum states of matter that can appear and can give you, surprises, the next question is how we model them, how we explain them, and what we have understood from them. And I want to argue in this colloquium that basically we've gone a long way in understanding the world around us from Aristotle and antiquity, where they basically had this garbled vision of what makes the world, which is these fire, air, earth, and then ether ideas that were going on before alchemy. So my field, which is condensed matter physics, basically deals with phases of matter. And everybody knows what a phase of matter is. A phase of matter, the classical phase of matter, are solid, liquid, and vapor. So from vapor, you cool down, you go to liquid, and then you cool down even more, and you go to solid. And this is kind of endemic in all systems, in all materials, all gases, all compounds on the planet Earth. But as you cool down in condensed matter physics or solid state physics, quantum effects start showing up. And depending on the temperature at which you cool down, some of these quantum effects can show up at higher temperature, some of them can show up at lower temperature. But depending on the temperature, you can get, for example, ferromagnets, which are the magnets that you stick on your fridge, and they involve the orientation of spin in the same direction two antiferromagnets, which you couldn't really see because they have spins up and down, and then even lower temperatures, superconductors, which are materials that basically run electricity without any loss, and that have phenomena such as levitation. You know, everybody's seen the levitation of a frog, and you know, anything else, even trains, as you build a strong magnet. All of these are basically proponent of the concept that superconductors try to expulse a magnetic field. So this is a purely quantum effect, and of course, a lot of physical effort is put into, in my field, is put into raising the temperature at which these quantum effects become important, so that you can build new technologies such as you know, room temperature superconductors, or room temperature electricity transport, and many other things. But at a very fundamental level, and coming back to the question as what we're made of, the only things you have to play around with in my field are the elements that exist in the periodic table. And you know, there's 100 and something elements, but there's only 94 of them that are appearing naturally in on planet Earth. So the other ones you can make in laboratory, or they're metastable, etc. But there's 94 of them that appear that you can actually get, let's say, quite easily. Some of them not that easily, but a lot of them very easily. Now, if you think about these 94 elements, you can then think about mixing them together. And nature has a way of mixing things together that, you know, depends on the potentials in between atoms, the radiuses of atoms, the electronegativity of atoms, all these concepts that have, you know, evolved in hundreds of years of chemistry. But as a fundamental problem, you can immediately see that the number of compounds that you can make is factorial or exponential. And the reason is you can make binary compounds, you can, from elements, but even a binary compound can have you know, more than one element, and because they have two, but they can have them in different stoichiometric ratios. Then ternary compounds, you can have three elements in different stoichiometric ratios. And I can go on. There's systems made out of 5, 4, 6 elements, etc. And these numbers, LMN, can also be big, from 1 to, say, 10 or 20, etc. So you can have an embarrassment of riches of materials, because each X chemical element, one of these 94, they can be binary, ternary, or many other compounds, and they can appear in different stoichiometric ratios. So you immediately see how you can get to a huge number of compounds. And for example, here, I'm just writing down the number, some compounds which are called Kagome lattices. These are a specific type of compounds in a specific symmetry group with a specific position of the elements. And you can clearly see, I wrote here, I don't know, about 50, but you can clearly see how they expand. There's hundreds of them just in this tiny little corner of the phase diagram of this of the number of compounds. And really, if you look at websites which are now fairly common, such as the ICSD website in Germany, or the Materials Project in the US, or other websites in Asia, there you can see that there's hundreds of thousands of materials that are tabulated. For example, the ICSD website has at least 300,000 materials that are made from these elemental compounds together, and they basically increase it at a rate of, I don't know, 5,000 per year, at a huge rate. So there's a huge phase space of materials that gets discovered, and one of the questions that you can ask is, how do we classify these materials? Or how do we put some order in them, or how do we understand them? So now that we've made them, or the chemists have made them, how do we understand them, and how do we make new ones with desired properties? So these are really three-dimensional materials. There's thousands, hundreds of thousands of them, and you really want to develop kind of a similar characterization of these materials that for example, Mendeleev developed in the periodic table of elements. So in the periodic table of elements, you immediately see that the elements are characterized by integers, which are their atomic number, their quantum numbers of the angular momentum, different shells, etc. This is the columns and rows of the periodic table, and you know that their chemical properties, reactivity, etc., are basically given by their position in this periodic table. The first thing that we would like to do is to put some order in these hundreds of thousands of compounds and classify them by some numbers that are very similar to the ones in the periodic table, i.e. by integers. But you can immediately see, as I said, that there is a huge variety, because we can build, simple compounds such as this one, or we can build many different lattices such as misfit compounds. And then we run into the trouble of not knowing what is a principle to characterize these materials and how to, build new ones. We can always do trial and error, but how to do it in a very predictive manner. So basically, this is what I'm going to be talking about, some advances in how to classify compounds first, and then going to be talking about how new ways of engineering compounds can make two-dimensional to three-dimensional multi-layer compounds that have many different states of matter. So let's start with the understanding of electrons in condensed matter physics. So on the left side, you can see the lattice of graphene. This is a single sheet of carbon, and it's a hexagonal arrangement. So you can see that there is a unit cell. This unit cell has two atoms and is repeated over the area of the lattice, a two-dimensional system. And it was, of course, first isolated in the early 2000s by Andrei Geim and Novoselov groups. They won the Nobel Prize for this. So this is really kind of one of the simplest materials you can have. And the way we understand materials, and this is, of course, also similar for graphene, the reason why I'm putting graphene now is, I'll come back to it later in these twisted samples, is through the behavior of the non-interacting electrons. So we first understand what a non-interacting electron does. So in each of these sites on the graphene lattice, on a hexagonal lattice, sits a carbon atom. This carbon atom has some electrons in its outer shell. These electrons in its outer shell have some energy. And unlike a single carbon atom where I have energy levels, or the hydrogen atom where I have energy levels of the electron, the fact that I now have a periodic lattice influences the energy levels of these electrons dramatically. So you don't really just have just single atoms with energy levels. You have a continuum of states described by a lattice momentum, which you can write in what's called the Brillouin zone, which is also hexagonal. It's just a Fourier transform of the real space unit cell. And in this Brillouin zone, the electrons have an energy, and this energy disperses, meaning takes different values depending on the momentum of the electron. So this, in condensed matter, we call dispersion. Of course, you have heard of dispersion for photons, for example. The energy of the photon is this, the speed of light times the momentum of the photon, which is related to the wavelength of the photon. So each photon has a clear energy. It's a gapless particle. And also these electrons in graphene are gapless particles. In fact, their Hamiltonian is just the Dirac Hamiltonian, which people in high energy physics know is the massless Dirac Hamiltonian in 2 dimensions, is its momentum times Pauli matrices. So this is a very simple Hamiltonian. Just the velocity, there's a velocity here, this velocity v is about 10 to the minus 2, the speed of light. So it's still very large because, the speed of light is huge. So for a condensed matter system, this velocity is still very large, which gives the electrons in graphene a very large dispersion. So that means that in these cones where they live, basically an electron of momentum k here has energy v times k. And electrons cannot live at any different energy than this. This is called the dispersion. An electron here acquires energy very steeply as the momentum is moved away from what is called a Dirac cone. So this type of band structures or dispersions are what characterizes the electrons in a solid. They're usually written as a function of the lattice momentum because it's a periodic system, which is just a Fourier transform, and they're akin to the dispersion of photons or the dispersion of a massive particle in some other systems. And graphene is really gapless Dirac fermions. Because in graphene, the dispersion is very large, meaning the kinetic energy of the electron as a function of momentum is very large. If I increase the momentum, I increase the kinetic energy a lot, then the kinetic energy will dominate. But in other systems, when we add interactions, if we can make interactions dominate, then the problem becomes basically unsolvable. Why is it unsolvable? Well, for single electrons, the problem is just solving a Schrodinger equation for a single electron. Schrodinger's equation for a single electron gives us this band structure. It's a hard problem, but it's not impossible. If I take a Schrodinger equation for, say, 10 to the 23 electrons, which is the number of electrons that I have in a sample, that is a problem that even on a computer to solve would need exponentially more qubits or more bits than the number of particles in the universe. And the reason for that is that if I have 2 or 3 electrons or 4 electrons or 5 electrons interacting with each other, the Hilbert space of these electrons becomes exponentially large in the number of electrons. And this is just the property of entanglement. It's a fundamental property of quantum mechanics. Entanglement means that the Hilbert space of many electrons varies exponentially in the number of electrons. And you can see, for example, with an electron spin, if I have 2 electrons on 2 sides, but with spin, I can have spin up, or 3 electrons on 3 sides, spin up, down, up, all of them, or the other one can be spin down, up, etc. So I can flip spin. So you can see I can have 2 to the 3 or 8 states. If I have n electrons just with spin up and down, I can have 2 to the n states. Once n becomes of order 60, 70, the Hilbert space has dimension larger number of particles in the universe. You cannot model it by computer. So interacting problems are particularly hard unless you have some approximation. And most of the physics in my field or cold atoms or other fields is finding approximations to quantum states of matter that you can model in a way that you get the physics out, but prevent this exponential increase of the Hilbert space. You can never prevent it, but you can find guided approximations that will give you the correct physics, even though you can't do an exact calculation. So single particle electrons dispersion, interactions, exponential challenges. But just in single particle dispersion, which are much easier to solve than interacting problems, even then, there is something very interesting that happens. And this is the concept of topology that's related to the electron wave functions. And this is something that basically has been developed in physics since the 80s with a huge uptick in 2005, 2006 with the discovery of topological insulators, where it was basically realized that there are materials that have topology without putting them in any external fields, without doing anything to them. And at the basic level, I don't have time to go through details, but the basic level, this advance that really kind of spun 2 decades of research is an understanding that the electron wave functions, which are solutions to Schrodinger's equations, are really given by, they really describe maps. So the electron wave function is a system that solves Schrodinger's equation. But since I have this momentum, this is single electron wave function for 1 electron. Since I have this momentum, I can ask, as I vary the momentum of the electron, what happens to my wave function? And it was realized kind of early on that if the momentum spans a closed manifold, such as a torus, which is the case when you have periodicity, when you have periodic structures, I can make a Fourier transform of a periodic structure. My momentum goes into the Brillouin zone, and it's also describing a closed manifold. This wave function, for example, can also describe manifolds. So as I vary the momentum on the torus, this wave function varies in some manifold, and hence it can be described by topology. So let me give you a very simple example of the wave function describing a manifold. Let's say I have per site, I have two orbitals. Okay, so if I have two orbitals, say S and P, I can describe the wave function of the electron to be in the s orbital and in the p orbital at each momentum by a two-component. This is my psi. Okay, and then you can immediately see that normalization tells you that psi1 squared plus psi2 squared has to be equal to 1. That's each of these has a real part and an imaginary part. This would form an S3 sphere, a 3-sphere, but actually Schrodinger's equation is invariant under multiplication by a phase. So I can multiply the left, right, and the right side by the same phase. That means I can make psi1 real. That means I can get rid of this absolute values. This is called the gauge transformation, and then it describes a 2-sphere. Because it describes a 2-sphere, that means that my wave function is really just a map between a torus and a 2-sphere, and then it also means that it's described by topological integers. So how do I see that it's described by topological integers? Well, it's very easy. What you have to do is ask what happens to this wave function as the momentum is varied everywhere around the torus. One thing that can happen is that this wave function does not cover the entire sphere S2. Okay, it can cover part of it, or it can cover almost none of it. So this is a wave function that sits only, for example, at the North Pole, okay, and doesn't move. What this means, it really means it's a wave function that looks like 1, 0. Okay, so it has probability 1 of the electron being in the s orbital and 0 being in the p orbital. This is what's called the band insulator, where the electron just sits as a function of k in the s orbital. That's the energy, and has no probability to sit in the p orbital. It's an insulator. It's the most boring type of insulator. The electron is just localized on the s orbital. This is how the wave function looks. Now, this is the boring wave function. We describe it by a topological number, which we call 0, which is how many times the wave function covers the entire sphere completely. At the other end of the spectrum is a wave function that covers the entire sphere completely as the momentum is moved around the torus. And this is a wave function that's described by a number which is 1, which tells you how many times each point on the sphere is touched by the wave function, or the wave function takes this value on each point of the sphere, or moves on this point of the sphere as I take the momentum around the torus. And notice that if I cover the sphere once, then there is no way to make it be covered 0 or anything less than 1, because in order to cover it less than 1, I would have to drill a hole, right? It's like wrapping a balloon around a sphere. To pop it, I would need to drill a hole. That's called a non-adiabatic process in my field in condensed matter, and I cannot do this. But basically, it's either the balloon is broken, either I put a needle through a balloon or I don't. If I don't put a needle through a balloon, I have an integer, which is called topological integer, which is 1. If I put a needle through a balloon, even the balloon might be a little bit, one disappear, but that's a topological integer 0. I haven't covered the entire sphere. Of course, unlike my analogy with balloons here, I can actually cover the sphere twice, 3 times, etc., by making the wave function move around the sphere at a higher rate as this k moves around the torus and covering it a few times. Now, I don't have time to go into details, but it was shown that actually just this simple topological concept that's actually kind of deep and characterizes wave functions has a clear experimental effect. And the experimental effect is that as I put a material described by a wave function with winding number 1, this is, for example, bismuth selenite, bismuth 2, selenium 3, for example, close to the vacuum is this topological number 0, then even if this system had absolutely nothing interesting in the bulk, or we thought it had nothing interesting in the bulk of the system, on the surface, you'll see electronic states that start developing. So these are surface states, okay? And these are bulk states here. Bulk states, bulk states. So these are electronic states that live in the bulk of the sample, okay? So these ones live here. The surface states live here. And these surface states, you can't get rid of them. There's electrons that live there. And even if I take a hammer and start smashing that surface or chemically do something to it, etc., I cannot move these electrons from there. So these electrons are forced to live there by the topology, and this is called the bulk boundary correspondence in condensed matter physics. Now, the other simple example of topology or topological integers is, for example, this winding in 1 dimension. The 2-dimensional example that I gave you before is a little bit more abstract to see, but this winding is very easy. For example, this wave function is exponential 2 to the ik. You can see that in order for this guy to come back to the same point on this trajectory, to the same point here, it has to wind twice. So this is an example of winding number. The winding number that I showed you in the previous slide is just kind of a generalization of this to the 2 dimensions. Now, for many years, from 1981, since von Klitzing discovered the integer quantum Hall effect, to 2005, 2006, it was thought that these systems with topological integers are basically confined to one case, which is the quantum Hall effect, which is electrons under a large magnetic field. Everybody has learned about Landau levels when they were young, and basically those electrons in a Landau level have a topological number, which is also the reason for the quantum Hall effect and the Hall conductance. Now, topological insulators, which is the first part of the talk today, topological insulators basically challenge this belief and showed that there are other systems that don't need to be put in a magnetic field that are described by topological integers. And these topological integers have an experimental meaning. They're equal to a number of edge states or number of surface states or number of corner states, etc., that the system would show if you do an RPES or if you take a quantum photography of the surface. On the surface, for example, this is bismuth, and this is an artist's rendition of bismuth, but you can see it's got these hinge states here. And this is a photonic crystal where you excite light, but in the bulk, you have a photonic gap, so you see no light, but on the edge, you see these edge states moving in, and this is because this is a photonic crystal with a topological number in the bulk, so it gives rise to the edge states. And basically, this topological integer is really the number of edge states or number of things that live on the boundary. So this was kind of a 2005, 2006 development, and it was remarkable for the very simple thing that in physics, or at least in condensed matter, not many things come out of theory being predicted and then discovered. Of course, there's many things that are predicted, but not discovered. Most of the times you find experimentalists find discovery, and then theorists try to explain it. But unlike previous eras of discoveries, these theoretical predictions came before experiments. So these integers, actually, for people who are doing more chemistry in the audience, can really also describe bonding of atoms. So for example, here I'm putting two boron atoms, but they might actually be carbon. Let's just put carbon because it's easier. So just graphene, for example, the same thing. Boron and carbon have similar properties in some compounds, but let's put carbon atoms here. And what we know about carbon atoms is that they have s and px, py orbitals, and we know that they have the concept of sp2 bonding. sp2 bonding just tells you that these atoms like to sit in an environment that has C3 symmetry, meaning there's three sites at 120 degrees, three bonds at 120 degrees from each other. These atoms sit in the middle, but because these orbitals, the sp2 orbitals, are strongly hybridized, these three orbitals, which really initially sit on the carbon atom, they can actually split across along the bonds. And because they split along the bonds, they can form 1, 2, 3. There's three orbitals on site. They're going to form three orbitals on the bonds. But now notice that there's another three orbitals coming from this guy in graphene, okay? And now notice what happens here. Here, no atom lives. This is called the Kagome site, but there's no atom that lives here. But when these two made up orbitals, because they're made up because they're just kind of a basis, a concept, a basis redefinition of these atomic on-site orbitals, when they meet together, they can form bonding anti-bonding pairs, i.e. positive and negative combinations of these two, and can form what is called sp2 bonding and anti-bonding states, which are the reason why graphene is actually such a sturdy material and its phonons are so high, etc. Now, these bonding and anti-bonding states is the concept of covalent bonding. And covalent bonding in chemistry was always kind of a not abstract concept, it was a very real concept, but it was always a murky concept in the sense that, you know, it wasn't defined as 1 or 0. In fact, many people have different levels of define different levels of covalences. However, through topology, we're able to define covalent bonding in an integer way. So it's either there or it's not. And then integer way is just how many orbitals do you have at this site, which is a site that is not associated with the initial atoms. So the initial atoms, i.e. the heavy ions, sit on the hexagonal sites, but the electron orbitals or Vanya states have moved to the middle of the site, and then the integer that describes how many states have moved there is a topological integer that describes covalent bonding. So this is a mathematical theory that allows you to basically define materials. What is it good for? Well, for example, you can predict where electronic states will exist with all these theories. So let's take catalysis. This is a simple catalytic, one of the very best efficient catalysts that we have, one of the best. But basically what you can see is that its catalytic properties depend on the surface at which you cut the material. So for example, here, there's no catalysis. You don't see any H2 bubbles accumulating. Here, there's no catalysis either on the surfaces. But on the hinges, where surfaces touch with each other, you can see heavy catalysis. The reason for this is that if I was to compute one of the topological integers of this material, it would tell me that the electron Vanya state has moved in between the atoms. Now, if it's moved in between the atoms and you cut a bond, i.e. make a surface, you can't cut through an atom because we can't split the nuclei. But you can certainly cut between the atoms by just, taking a knife and cutting, or by splitting the material. So if you cut in between the surface, the two atoms, a surface in between two atoms, but the electron state has moved and sits exactly in the middle of the two atoms, then you're going to get electronic states of the surface and hence catalysis. So what I want to argue is that all these topological concepts are very good for predicting many physical properties, including something as practical as catalysis. So fast forward a few years from 2005 to 2006, 5 years meaning 10 years, and it soon became obvious that basically this is not only a concept, topology is not only a concept that applies to, one, two, or a small number of materials, but it's basically a concept that can be used to classify all the materials in nature. It's not a unique classification. A lot of materials have, given by the same topological integer, can exhibit different properties, but it's certainly a classification which gives some integers or a series of integers, such as the ones given here, to a material. And whenever this integer is non-zero, you're going to have some spectroscopic properties of this material at different boundaries. So this is a non-interacting classification. So now what happens when we add interactions? So then all hell breaks loose. And the reason why all hell breaks loose is because of this exponential increase in the Hilbert space, or entanglement is really what Einstein taught us, is really entanglement, the reason why we cannot solve it. But if the kinetic energy is larger than the interactions, or much larger interactions, then we basically don't care, because kinetic energy of electron 1 adds up to kinetic energy of electron 2 adds up. So those, in terms of kinetic energies, it's a very simple problem. It's just additive. When I add interactions, then the electrons start talking to each other, and this becomes an unsolvable problem. But if the kinetic energy is large, then interactions won't matter. So one way to make the interactions important is to make the kinetic energy small. Now, there's several ways of making the kinetic energy small. One of them is by just putting the electrons in a very large negative quantum well, or potential, so they just sit there and they don't move. That's not a very interesting way of making the energy, the kinetic energy small, but there's other ways of making it which are more interesting. For example, in these Kagome metals, where the electrons, either the atoms or the electron center, sits in the Kagome site, which is this one, for example, you can clearly see the presence of what we call flat bands, i.e. bands. This is a band structure of this material. This is how basically band structures look in nature. Okay, so these are the allowed energy levels of this material. The reason why there's so many is nickel has d orbitals, so 5 d orbitals times spin, so 10, but there's 3 nickel per unit cell, so you already have 30 orbitals, so at least 30 bands. Okay, so it becomes a spaghetti of bands, but you can clearly see that even though you have a spaghetti of bands, there's some bands which are basically flat, i.e. do not disperse as the electron moves, the momentum of the electron moves around. But you can see that the reason for this non-dispersion is not that the electron is pinned at sites. Why? Because if it was pinned at sites by a negative potential, then no electrons could move from one side to another. Okay, if no electrons could move from one side to another, then the energy of the electron would just be the energy per site, some negative energy, so you wouldn't have any dispersion. But you can see that many bands here do have tons of dispersion. This is electron volts. It's a huge dispersion. So you can see that even though there's many bands that have dispersion, then you do have hopping. The electrons are not pinned at sites, but you still have some flat bands. And the reason for this is quantum interference, is basically the fact that these wave functions of the electron, as you look at the different sides of the lattice, take signs, because it's quantum mechanics, and these signs are in such way that when the electron comes back to itself, they cancel out. Okay, so that gives no dispersion, and these are called flat bands. And now we expect in flat bands to have interactions become important. But most of the flat bands that exist, as I showed you here, in 3D materials are a spaghetti, right? So basically, you can look here, there's tons of many flat bands here. And the reason for this is, again, I said too many orbitals. Now, if we are going to do physics on a spaghetti, it becomes much harder to understand what's going on or to find principles because there's too much noise. There's too many bands, too many electrons, too much noise disentangling, both in experiment and in theory, disentangling what's universal from what's not universal. So this is where Moire comes in, and this is really kind of like the alchemy of today. So the Moire field is basically creating bands with large interactions, but without having a spaghetti of bands. So they're very clean, or at least much cleaner than in 3 dimensions, where there's many other bands. And there's even an added advantage, you can manipulate them. So Moire is a term that shows up from what the kings of Europe used to do back in the days, which is to make a lot of money and make a lot of silk rooms where they would put different patterns that you would then see as you moved around. But basically, in physics, it consists of taking 2 or more, we're just going to focus first, 2-dimensional materials and doing small deviations to them. Small deviations meaning you take 2 of them, you stack them on top of each other, and then rotate them by a small angle. The first thing that was done is graphene, which is still kind of like the grandparent of all these. And in graphene, what this does, and I'm going to go a little bit faster, is to take this huge dispersion that I showed you before, right? This is dispersion that I told you is basically this is basically 6 electron volts. And notice that as you twist 2 layers of graphene by a small angle, 1 degree, okay, 1 degree, you're going to get a new periodicity, right? You can see clearly the new periodicity. So the unit cell becomes much larger. But then because the unit cell becomes much larger, the momentum space becomes much smaller. And remarkably, what happens is that the bandwidth of these 6 electron volts that I've argued exists here transforms into a bandwidth of 6 milli-electron volts. So it's 1,000-fold reduction of the kinetic energy. Okay, so the kinetic energy has reduced 1,000-fold just by doing these small things. And that means that now we have a chance of interactions becoming important. In graphene, people have tried, Philip Kim, Efetov, many other people after them have tried for a long time to induce interactions in graphene. It's very hard to do because of this large dispersion, means the density of states of electrons here, where the Fermi level is very low. But now, when I take these 2 layers and rotate them by 1 degree, because I have flat bands, so no kinetic energy, okay, then interactions become important, and hopefully you can get interacting states of matter. And remarkably, this is the case. And the physics here, which I'm going to go very fast through, is the following. This is an example of the band structure of graphene in the Brillouin zone, i.e. the momentum of the Moire lattice, for twisted bilayer graphene at the magic angle, meaning at this 1 degree for which the bands become 6 milli-electron volts dispersion. You can see it's 6 milli-electron volts dispersion. This 6 milli-electron volt dispersion, there's 2 bands here, so I can put 2 electrons per unit cell. They can occupy 2 electrons per Moire unit cell, per this large unit cell. So that's a very tiny proportion of electrons per the original graphene unit cell, which is very tiny. But I also have 2 spins and 2 valleys, meaning valley K and K prime. So that's a factor of 4. So I can put 8 electrons in these bands, and the numbering of the band is going to be -4 in this single particle gap to +4 here, a difference of 8 electrons that I can fill these bands with. So if my Fermi level was, for example, here, let's say -3.5 electrons, okay, I would cross electronic states in the single particle picture. So my system should be a metal anywhere at any filling between -4 and 4. But here's a plot of the resistivity versus filling. This is the filling, okay? 2, 3 of these bands. And here's the resistivity. And you clearly see the resistivity exploding at filling, for example, at integer fillings. Resistivity exploding means the system doesn't want to conduct electricity, means the system is insulating. So this is a purely interacting effect, because in single particle, the system should be a metal here. And moreover, you can see superconductivity in between these integer fillings of the bands, of these bands. So if I'm at around between -2 and -1, I can see some superconductors, etc. So there's clearly, now we have a first example of a system where the bandwidth has kinetic energy has quenched dramatically, interactions become important, and now you have completely different physics. Now, there's even more of a puzzle in this system, and this puzzle comes from, taking quantum snapshots of the system. So if I take an STM, this is Ali Yazdani, Eva Andre, many other people who did STM experiments. This is the length of the Moire unit cell. This is roughly 10 nanometers at 1 degree, or 12 nanometers. But now you can see that with my Fermi level parked in these flat bands, you can see that the quantum picture of the system looks like it has localized states on the triangular lattice. So even though graphene has a hexagonal lattice, this looks triangular, and it looks like it's really localized electrons on the triangular lattice. So it looks like this system is just highly localized electrons, but we also know from Pablo, from Efeto, from Philip Kim, from Andrea Young, many other people, Amir Jacobi, we also know that this system is not just localized states, because localized states could not give me superconductivity, could not give you metallic behavior. So we know the system is very different from localized states, but it looks very strange. So in a famous paper, it was basically said that this correlated state features contradictory properties, some associated with itinerant electrons and others with localized moments. I don't have time to go through the details, but what I want to argue is that this system is the perfect quantum simulator for a new state of matter that's called a Mott semi-metal. And basically, I'm just going to go very fast through here. It turns out that you can actually think of these 2 flat bands, which are here, which in experiments look both localized and delocalized. You can think of them as being made, 95% of them, out of localized electrons, and these localized electrons sit exactly where those blobs, yellow blobs in STM in the quantum picture were sitting, plus 5% of the bands made out of delocalized electrons, which look like AB untwisted graphene. Okay, so the twisted sample looks like some untwisted delocalized electron, which is gapless at the gamma point, okay, at the center of the Moire-Briand zone, plus a localized electron. So now you immediately, once you make this mapping, you immediately realize that the system looks like what's known as an Anderson model. An Anderson model is something that Phil Anderson introduced a long time ago to deal with the Kondo problems, etc., was an unsolved many-body problem for at least 50, 60 years. The reason why it's unsolved is the same exponential increase of the Hilbert space. But now we have a system that looks very much like an Anderson model because it's got these localized moments plus these itinerant electrons, looks very much like an Anderson model, and we can do experiments on. So we can understand the physics of this model, and remarkably, new experimental techniques such as this quantum twisting microscope, which can get the spectral function, i.e. the imaginary part of the Green's function of the electron at any energy and momentum. So it's a momentum and energy resolution, which is something that's a new development. There's only two in the world. They can get the spectral function of the system. And to make a long story short, the spectral function looks very different from the non-interacting band structures. Non-interacting band structure at different momentas in the Brillouin zone looks gapless, for example, at the Moire K, gapped, i.e. two different states at momentum gamma, but the predicted spectral function looks exactly the opposite, gapped by the interactions at momentum K and gapless at gamma. And now this is the spectral function that the experiment sees, the one below, and you can immediately see that it matches the one predicted. And this is kind of the first really momentum space visualization over an entire Brillouin zone of some Mott Hubbard bands. Now the system is actually a Mott semi-metal because this itinerant fermion at gamma is gapless, but I won't get into the details of this. How much more time do I have? Maybe 5 minutes?
How long? I don't know how long. Maybe I think you can go ahead.
5 minutes is good?
Okay. 5 or 10 minutes, I think. Okay, yeah.
Okay, very good. Thank you. Okay, so that was the first thing. So twisted samples are given, are a quantum simulator, bilayer graphene for what's called a heavy fermion system made up of localized moments coupled to a gapless fermion. But then, of course, much more recent development was the fact that the quantum Hall effect and its fractional counterpart were actually observed with zero magnetic field. So, of course, everybody in the audience knows that if you put electrons in the magnetic field, you have Landau levels. If you can now gate the Fermi level in between Landau levels, your Hall conductance, i.e. sigma xy, which is the ratio of the X current over the Y magnetic over Y electric field, is quantized to integer times E squared over H. And this integer is quantized to better than 10 to the minus 12. It's actually the standard for quantization for measuring E squared over H in the world now. So it's a very well quantized integer. Of course, it's so well quantized because it's topological invariant, not because the sample is clean. For example, this is how the sample looks, where the quantum Hall effect was measured at the beginning, and it gives you an amazingly good quantization of the Hall conductance in terms of this topological integer. So this integer is equal to the number of edge states, etc. But now, if I go put my Fermi level in between, not in between Landau levels, but within a Landau level. So this is a Landau level here. Okay, and I put my Fermi level within a Landau level at fractional fillings, I will see the Hall conductance quantized not in n times E squared over H, but in some ratio of rational natural of integers, so a rational number, P over Q E squared over H. So for example, here you can see that I have the Hall conductance quantized at 1/3 E squared over H, right? Because the Hall resistance is 3, so the Hall conductance is 1/3. Hall conductance 1/3 basically tells you that the carriers in your system are not charged E electrons, but are charged E over 3, because you're having some electrons carry 1/3, and then you have 2/5, etc. So this 1/3, Tsui, when he first found it, said, oh, these are quarks. But basically, all of these are under a magnetic field. You can clearly see the huge magnetic field here, 30 Tesla. Now, it was proposed more about 12 years ago that you don't actually need a magnetic field. All you need to do is take one of these topological Chern insulators, say the Haldane model, and fractionally fill the band. And in theoretical studies of these interacting models, you saw these degenerate ground states. These are a diagonalization of the models, degenerate ground states separated by a gap from a continuum. And this is kind of a hint that something interesting like the fractional quantum Hall effect happens, but without any magnetic field. Now, these predictions were basically, people thought they were la la land predictions. They were never going to get realized because they were on, very unrealistic models. And you needed many things. You needed interactions to be, stronger than the bandwidth. You needed not only interactions to be stronger than the bandwidth, but you needed to basically put the Fermi level, have controllability of the Fermi level at 1/3 or some rational number of the band where a many-body gap would open. So this was basically thought to be impossible, but it's not. And this is Xiaodong Su's group first, and then Qinfei Mak and Jie Shan's group, and now others in MOT2. In these twisted samples, as I've argued, immediately interactions become very important by just the nature of the quenching the kinetic energy. Now, topological bands, i.e. bands given by topological integers, such as the Chern number, such as the Landau level type integer, can also appear immediately in these bands. And without a magnetic field here, people saw immediately the fractional Chern insulator, i.e. fractional quantum Hall without a magnetic field at, for example, Hall conductance 2/3 E²/h. Now, there's also very interesting developments in rhombohedrographene from Longju's group and Xiaobolu at Peking. But basically, in this system, what I want to argue is that this system is completely not understood so far, and it's very new, unlike any other of the fractional Chern insulators, because this system actually is gapless. So it's not just a band like a Landau level, where I fill it at 1/3, but I have a flat band at the bottom, but then I have a gapless region of states, and the fractional Chern insulator is still seen at a fractional filling of this bottom. This system is completely not understood, and hence there's room for theoretical development here also. Okay, to close with is I've presented two systems which are or three systems, right? Twisted bilayer graphene, molybdenum diterorite, and then there's a rhombohedrographene, which are, there's results. People have twisted them. In one of them, they see heavy fermions, Mott Hubbard bands, Mott semi-metal, and the other one, fractional Chern insulators. But if you look at the number of materials that admit two-dimensional single layers, there's about 9,000 computed them. And this is from Nicolas Mazzari's database, but there's, you can get them at our database where you compute the topological index. We took Mazzari's database and computed the topological invariance for these single layers. Now, out of these 2D, 9,000 2D materials, maybe not all of them will exist, but certainly a large part, at least 200 already have been exfoliated out of these, and the prediction is that many thousands more can be exfoliated. So let me give you an example. So these are some materials in this database that have now been exfoliated by either Leslie Shoup or Claudia Fels or Dima Efetov or Qinfei Mak's group, etc. So you can see that there's many materials that like these ones, for example, that this is how they look. Then they can be exfoliated to single layer. Now, if I have these many materials that can be exfoliated to single layer, I can actually make twisted samples. I can take 2 layers and I can make homo, meaning the same layer, hetero, hetero meaning 2 different layers, 2 different materials, etc., layers of twisting, and obtain different band structures. All I need in order to be able to predict things is to start with some nice band structure at the beginning. So for example, this is tin selenite 2, and you can clearly see how it has a super nice band structure here at an endpoint minimum. So this one, I can hope that because the single layer has such a clean dispersion, I can hope that if I twist this material, I'm going to get a nice and clean dispersion. Also notice that this twisting is that of a completely different point than in graphene. This is the endpoint. In graphene and in MOT2, we are twisting the K point. The difference between these crystallographic points, which might not mean more in principle, is actually dramatic because the symmetries and the different Hamiltonians act differently. So indeed, if we twist these, what happens is, this is a calculation, this calculation takes about 6 months to do. You can clearly see that at small angle, flat band emerges, okay? And in this flat band, if you then do, because this flat interactions will take over, and if you compute the influence of the interactions and the Hamiltonian that you get from the interactions, you will get the Hamiltonian of a TJ model, i.e. TJ model that's one-dimensional, so 3 of them because of the endpoint. So this model, to make a long story short, acts as a simulator for a quantum spin liquid. So this is just one other material, and already we have a completely different class. This is not experimentally done yet, but people are working on it. But theoretically, it's a completely different class, which is simulated for a spin liquid. Now, I thought, spin liquids would never be found experimentally, with the exception of ruthenium chloride, etc. But with these Moire samples and with the controllability that they have, I think that they might. So now, just to close, I hope I convinced you that basically 2 things happened. In materials and in quantum physics, we can use integers to classify the systems, and then we can manipulate these integers by going to new engineering of quantum systems in 2 dimensions, which involves moire or twisting or doing things to the samples controllably. And we can get many, many phases and all in the same system. So we can get fractional translators, superconductivity. We get magnetism insulators in the same system, which you can controllably then tune between by gate doping. So you don't need to dirty your system in these 2 dimensions. And the intersection of all these phases of matter can hopefully bring things such as anion, quantum computing, or many other, hopefully, functionalities, optoelectronics, terahertz sensors, because the gaps are so small. So hopefully this has practical advantages, but from what I'm interested in, they're just a spectacular playground for many body physics. So with this, I wanted to basically thank my people that are sponsoring me, and thank you for your attention.
Yeah, okay. Thank you very much for your wonderful and insightful presentation. So is there any questions? Okay, so I ask one question. So why there is a strong correlated same metal? I remember in slides that are related to the topological heavy fermion. Yeah.
Yeah, so that's a very good question. So basically, the issue is that you can model this. I mean, it's not just a modeling. It's basically derived. So basically, what happens is that and the derivation, matches the experiment. But basically, these quantum dots that look here are the heavy fermions. So they're actually just some flat bands, okay? But because they're so localized, they carry a lot of the interaction. So because they carry the interaction, when the Fermi level is, say, in between them, they don't like to sit at the Fermi level. They can gain energy by splitting. One of them splits up, the other one splits down, and they gain energy, which is proportional to the interaction. Okay, the interaction is large here because they sit on the same side. Now, the other component of this system, 95% of the system is made out of these bands, but the other component of these flat bands is this gapless fermion here. It's a gapless fermion here that looks like AB untwisted bilayer. Okay, and this is responsible for, superconductivity, metal, etc. Now, if I draw this here, okay, it looks, that's at the gamma point, it looks something like this, okay? The horizontal axis is momentum. And then, of course, these guys, you can derive the term between them. These guys experience level repulsion. So they won't just cross here. These crossings will split. And then the final structure, the final band structure will look like this. Okay. So you're going to see these Hubbard bands, which are here, but you're also going to see the gaplessness of this electron here. And this gaplessness is protected by symmetry. It's actually a topological origin, which is the reason why, I link this with topology. It's this crossing can never be split unless you break the symmetries of the system. And that's what gives you this crossing here. It's a protected crossing, just like a Dirac point is protected by symmetry. This is also protected by symmetry. So that's why here is just very localized bands, but as you go towards the gamma point, they become highly delocalized. And this crossing is protected by symmetry. You can never gap it.
Okay, I see.
Thank
Thank you for your explanation. So is there any other questions?
Yes, I'd like to ask one question. So having many interesting phenomena in one material is a very interesting from experimental side, but what is the main achievement through this material from theoreticians' perspective?
Yeah, so I mean, for example, this type of Mott bands were not known. So there's several things. So my hope is that we can find states of matter that are not known. That's the academic theory hope, right? And the first example that we looked at, which is twisted bilayer, has this because right in just the Hubbard model for high temperature superconductivity, etc., at half filling, you just have two Hubbard bands. They look like this. There's nothing, there's a semi-metal in between. Here, the Hubbard bands look like this, but then around some point in the Briand zone, gamma, they become extended. So, it's a new state of matter. It's not just a Hubbard band, it's a Hubbard semi-metal. So basically, there's the zeroth, even this is just at half filling. So then I can, experimentalists can put a gate on the system and tune the filling, and we can see what happens, for example, when you dope such an Anderson model, right? The physics of an Anderson model at different fillings is not known. We don't know, we don't have an exact solution, especially when you have many flavors, etc. Even numerical solutions fail when you have many flavors, etc. So we don't know what the physics is, but here it's very easily manipulated and by experimentalists. So I hope it goes both ways, so we can understand something. We can use it as a quantum simulator of what the physics would be, for example, in an Anderson model, and we can predict things. For example, the spectral function was predicted, and then this quantum twisting microscope found it. But hopefully in other systems, it will go the other way around. So we can learn something, we can simulate, novel quantum systems. Then for example, in rhombohedral graphene, this is a remarkable system because the flat band, i.e. the flat portion of the band, is not, you don't have, several flat bands or even flat band separated by a gap from another band. You have really a gapless dispersion. So understanding how a gap state can appear in a gapless dispersion, how a gap topological state can appear in a gapless dispersion, is not understood. We never have, when you have Landau levels, they're just one Landau level, there's a single particle gap between them. But here, all the you have a flat bottom and then highly dispersive walls, but the situation is very different from a Landau level. So why do we see fractional quantized conductance here? And these are just in the experiments that exist. There's new stuff. But then for other, right, basically there's many universality classes of systems. You can twist, you can twist the endpoint. You can twist, for example, in a square lattice, you can twist these points. The Fermi level is there. So there's many classes that will give you different Hamiltonians that with different degrees of freedom that will give you different states of matter. So we don't know the full extent of this possibility, especially since the phase space is huge, because you can take two materials, three, same, different, you can twist them by a continuum angle. So just from a purely theoretical standpoint, it's also very interesting, I think.
All right, thank you.
Okay, so is there any other questions?
Okay, can I give a question? Can you hear me?
Yes.
Okay. Thank you for a nice talk. Let's say you talk about this Moire, very small angle twist case, but can this argument theory can apply to, let's say, for two different layers of little lattice mismatch?
Yes.
Like Moire patterns. Can you expect the similar things?
Yes, so that's a very good point. Yeah. So normally, yes. Have you finished your question, or did I interrupt you?
I'm finished. Yeah. Okay.
Okay, good. Yeah. So normally, you're certainly correct. So for example, in rhombohedral graphene, so ABC AB, there's a twist with the boron nitride that is being done about 0.7 degrees. Okay, and only when it's twisted and aligned do you see fractional churn insulator. Now, even if I didn't twist boron, if I didn't twist by 0.7 degrees, boron nitride would have a different lattice structure. So if I align it even at 0 degrees, you will get a okay. Now the only difference is that if I have the same lattice, so graphene twisted, the relaxation. So once you twist, the atoms don't like to sit in position, so they relax. The relaxation is a bit different in when I twist from just lattice mismatch and no twisting. One of them, for example, has a curl, the relaxation vector, the other one doesn't. So it's like details, but overall, I would expect that, yes, similar phenomena. I mean, similar phenomena, interesting phenomena. Okay. I cannot say that exactly similar phenomena would happen even with lattice mismatch, because relaxation is different. One of them is axial, the other one is longitudinal. But what I could say is that one would expect also very interesting things to happen just from lattice mismatch.
Okay. Okay. Good.
Yes.
Okay, so is there any other questions? Okay, so if there is no other questions, let's thank again to Professor Andrei Bernevig for this nice presentation, and thank you to everyone for your support to the APCTP Colloquium. Okay, thanks.
Thank you so much.
Mm.
Appreciate it. Thank you.